To completely describe the magnetic field at any point on the surface of the Earth, we have to specify its three elements at that point, namely declination, d, angle of dip or inclination, I, and horizontal component of the Earth's magnetic field, He. Let us study about these three elements in detail one by one. First, the declination. We all know that the Earth is spherical in shape. On this spherical surface, we can draw an infinite number of imaginary circles passing through the Earth's geographical north and south poles. All these circles have one common diameter, which is the line joining the geographical north and south poles, or the Earth's axis of rotation. These imaginary circles are called longitudes. Each of these circles, along with the Earth's axis of rotation, can be drawn in one plane. This plane is called the geographic meridian. The geographical meridian, when viewed from top, appears to be a straight line. Similarly, we can obtain the magnetic meridian by drawing a line from the magnetic north and south poles. This magnetic meridian also looks like a straight line when viewed from the top of the chosen point. At any given point, the geographical meridian and the magnetic meridian together look like two intersecting straight lines. The acute angle between these two straight lines is known as declination. It is denoted by the capital letter D. Declination changes from place to place on Earth. Declination is minimal at the equator and goes on increasing with latitude. The second element of the Earth's magnetic field is the angle of dip or inclination. A magnetic compass needle is provided with a pivot such that it can rotate freely about a vertical axis. The needle comes to rest when aligned with the magnetic meridian to indicate the magnetic north. If the needle were also provided with a pivot such that it can rotate freely about a horizontal axis, it would also rotate in the magnetic meridian plane. If the compass is placed in the northern hemisphere, its north end dips down from the horizontal position. If the compass is placed in the southern hemisphere, its south end dips down from the horizontal. The angle through which it dips with respect to the horizontal plane at that point is known as the angle of dip or the inclination, denoted by the capital letter I. In other words, inclination is the angle that the total magnetic field of the Earth, BE, makes with the horizontal surface of the Earth at a given point. The inclination is 0 at the equator and increases as the latitude increases. If this compass is placed atop the magnetic pole, it will come to rest in the vertical position. We can measure the inclination at any given point using a magnetic needle with the horizontal axis and a spirit level. The study of these elements help us to find the total magnetic field of the Earth, BE. To find BE at any point on the Earth, we take the help of the third element, the horizontal component of the Earth's magnetic field, HE, at that point. BE and HE are vectors. Let us now construct the vector diagram using all the three elements. Locate point P on the globe at which you want to determine the Earth's total magnetic field, BE. Draw a circle passing through the point P and the geographic north and south poles. This is the geographic meridian circle. Draw another circle passing through the point P and the magnetic north and south poles. This is the magnetic meridian circle. Draw a plane which is tangential to the sphere at point P. Draw a tangent PA to the geographic meridian circle at point P. PA lies on the tangent plane and represents the geographic north-south direction. Draw a tangent PB to the magnetic meridian circle at point P. PB also lies on the tangent plane, but represents the magnetic north-south direction. Construct a parallelopiped passing through P, A and B. Rotate the line PA in the tangent plane such that it touches the parallelopiped at B. This angle of rotation is the angle of declination D at the point P. The length of the line PB, to some scale, represents the magnitude of the horizontal component, HE, of the Earth's magnetic field at the point P. Rotate the line PB in the vertical plane such that it touches the parallelopiped at C. This angle of rotation is the angle of dip, I, at the point P. The line PC represents the magnitude and direction of the total magnetic field, BE, at the point P. Drawing this three-dimensional diagram is a cumbersome process. Instead, we can draw a two-dimensional view of the essential elements to determine the Earth's total magnetic field. Take only the plane represented by PBCD in the three-dimensional view and draw a two-dimensional view of triangle PBC. Draw a horizontal line PB with the arrowhead at B. The length of this line, to some scale, represents the magnitude of HE. Draw a line PC making an angle I with PB. Draw a line BC is perpendicular to the line PB with an arrowhead at C. Line BC represents the vertical component VE of the Earth's magnetic field. On the line PC, put an arrowhead at C. Line PC represents the total magnetic field BE of the Earth at the point P. We can now write the trigonometric relationships for the sides and the angle in the right-angled triangle. Sin I is equal to BC divided by PC, which is equal to VE divided by BE, or VE is equal to BE sin I. Cos I is equal to PB divided by PC is equal to HE divided by BE, or HE is equal to BE cos I. Tan I is equal to BC divided by PB is equal to VE divided by HE, or VE is equal to HE tan I. Let us start with some general facts related to magnets. A freely suspended bar magnet oscillates for some time and then comes to rest along the magnetic meridian in the direction of geographic north and south. One end of the magnet points to the geographic north pole, called north-seeking pole or north pole of the magnet. At the other end points to the geographic south pole, called south-seeking pole or south pole of the magnet. This is because the Earth behaves as a huge bar magnet with its magnetic north pole located near the geographic south pole, and with its magnetic south pole located near the geographic north pole. We know that the like poles of two magnets repel each other, and the unlike poles attract each other. Thus, the north pole of the magnet is attracted by the Earth's magnetic south pole and vice versa. If a bar magnet is broken into two pieces, we get two similar magnets with a decrease in the magnitude of their properties. Thus, the magnets always exist in dipoles. Isolated magnetic monopoles do not exist. This implies that isolated magnetic north pole or south pole does not exist. Let us now discuss an activity about the magnetic field lines of a bar magnet. Consider a glass sheet with some iron filings sprinkled on it. Bring the bar magnet from the bottom of the glass sheet close to the sheet. As the magnet is brought close to the glass sheet, we observe that the iron filings on the sheet arrange themselves as shown. If we draw lines along the orientation of the iron filings, the lines will represent the magnetic field lines. Similar field lines are observed in the case of a current-carrying solenoid and an electric dipole. Let us now learn about the properties of magnetic field lines around a bar magnet. The field lines of a magnet start from the north pole and end at the south pole externally, which is outside the magnet. But internally, that is inside the magnetic field lines start from the south pole and end at the north pole. Thus, the magnetic field lines of a magnetic dipole are continuous closed loops. In the case of an electric dipole, the electric field lines start from the positive charge and end at the negative charge. Unlike magnetic field lines, the electric field lines are not closed loops. They are open curves. The field lines give us a visual impression of the magnetic field. If we draw a tangent to a magnetic field line at a given point, it represents the direction of a resultant magnetic field at that point. The magnetic field lines never intersect each other, because the resultant magnetic field at a point has only one direction. If we assume that two magnetic field lines intersect at a point, then the resultant magnetic field at that point would have two different directions, which is not possible. The magnitude of magnetic induction, which gives the strength of the magnetic field, is obtained by the number of field lines passing normally through a given area. If the number of field lines passing normally through a given area is large, then the field is considered to be strong. It is similar to strength of an electric field. If the number of field lines passing normally through the area is less, then the magnetic field is considered to be weak. An alternative method of plotting the field lines of a magnetic dipole is as follows. Take a bar magnet, which is nothing but a magnetic dipole, and place it on a sheet of paper, which is placed on a horizontal surface. Then place a small magnetic compass at the north pole of the magnet. Plot a point on the paper indicating north of the compass needle. Shift the compass such that the south of the compass needle is observed at the plotted point. Then, again plot another point at the north of the compass needle, and then shift the compass as done earlier. Repeat the process to plot different points on the sheet around the magnet and note down the orientation of the compass at each position. We observe that the series of points plotted on the sheet are directed from the north pole of the magnet to its south pole. By connecting all the points, we get the magnetic field lines due to the magnetic dipole. The direction of the compass at different points on the field lines gives the direction of magnetic field at that point. Let us now learn the similarities between a bar magnet and a solenoid by comparing the magnetic induction of both. Finite number of continuous turns of a conducting wire wound in a helical shape represents a solenoid. We learnt earlier that the magnetic field lines of a bar magnet are similar to the field lines of a solenoid. Hence, a bar magnet can be assumed to be the same as a large number of current-carrying loops placed adjacent to each other. The two faces of the solenoid are similar to the poles of a bar magnet. The field lines leave one face of the solenoid into its exterior, and hence, this face of the solenoid is like the north pole of the bar magnet. The field lines enter the solenoid at the other face, and hence, this face is like the south pole of the bar magnet. Thus, the magnetic field lines of a solenoid are continuous closed loops similar to the field lines in the case of a bar magnet. We learnt earlier that if a bar magnet is cut into two pieces perpendicular to its length, two small bar magnets are formed. Similarly, if a solenoid is cut perpendicular to its length into two parts, two solenoids of smaller length are obtained. The two solenoids produce weak magnetic fields around them. Thus, each smaller solenoid acts like a small bar magnet. To make it more clear that the field due to a solenoid is similar to that of a bar magnet, we calculate the magnetic field induction B at a distant point on the axis of the solenoid and compare with the magnetic field induction at a point on the axial line of a bar magnet. Consider a solenoid of finite length with n turns per unit length. Let A be the radius, 2L be the length, and I be the current passing through the solenoid. Let the solenoid be placed such that the axis of the solenoid is along the x-axis of the coordinate system, and its center coincides with the origin. Then, the left end of the solenoid lies at the position -L, and its right end at +L. Let us consider a point P on the axis of the solenoid, and let R be the distance from the center of the solenoid to that point. To calculate the magnetic field induction B at the point P on the axial line of the solenoid, consider a small element of the solenoid of thickness dx, located at a distance of x from the center of the solenoid. Then the distance of the point P from the small element of the solenoid is r minus x. As n is the number of turns per unit length, the number of turns in the small element of the solenoid is equal to number of turns per unit length into length of the small element of the solenoid. That is equal to n into dx. We learnt earlier that the magnetic induction B on the axis of a current-carrying circular loop at a distance x from the center of the loop is equal to mu naught Ia square by 2 into x square plus a square whole power 3 by 2. Thus, the magnetic induction due to the current passing through the small element of the solenoid at the point P on the axial line dB is equal to mu naught n dx IA square by 2 into r minus x square plus a square whole power 3 by 2. The total magnetic induction due to the solenoid can be calculated by dividing the total length of the solenoid into number of small elements, and by integrating the magnetic inductions due to all the small elements, we get the total magnetic induction due to the solenoid. When we consider the small elements of the solenoid from one end to the other, the distance of the elements from the center of the solenoid varies from -L to L. Thus, the total magnetic induction at the point P due to the solenoid is B is equal to integral -L to L dB. That is equal to integral -L to L. Mu naught n dx IA square by 2 into r minus x square plus a square whole power 3 by 2. But IAN and mu naught are constant. Hence, the magnetic induction B is equal to mu naught n IA square by 2 into integral -L to L dx by r minus x square plus a square whole power 3 by 2. When we consider the point on the axis of the solenoid at a large distance, r is much greater than a, and r is much greater than x. Hence, we neglect the terms a and x in the denominator of the expression for B. Then, B is equal to mu naught n IA square by 2 into integral -L to L dx by r cube. But the distance of the point P from the origin r is constant. Thus, B is equal to mu naught n IA square by 2r cube into integral -L to L dx. On integrating and substituting the limits, we get the magnetic induction B is equal to mu naught n IA square by 2r cube into 2L. By multiplying the numerator and denominator of the expression with pi and rearranging the terms in the expression, we get the magnetic induction B is equal to mu naught by 2 pi into Ni2L pi a square by r cube. We learnt earlier that a current-carrying loop behaves like a magnetic dipole, and its dipole moment is given by M is equal to I into A, where A is the area vector of the loop. The solenoid consists of n number of loops per unit length. I is the current through the solenoid, and A is the radius of each loop. Thus, area A of each loop of the solenoid is pi into A square. The total number of loops in the solenoid is n into 2L, and hence the magnetic moment of the solenoid M is equal to N2LIA, which is equal to N2LI pi A square. Substituting M for the terms in the expression for magnetic induction B, we get the magnetic induction B is equal to mu naught by 2 pi into M by r cube. On multiplying the numerator and denominator with 2, we get the magnetic induction B is equal to mu naught by 4 pi into 2m by r cube. This is the same expression that is used to find the magnetic induction at a distant point from the center of a bar magnet on its axial line. Thus, a current-carrying solenoid and a bar magnet produce similar magnetic fields. Therefore, a solenoid is equivalent to a bar magnet, and their magnetic moments are also equal. If the magnitude of the induction they produce at given distant points from their centers on their axial lines is equal. The Earth abounds with a variety of elements and compounds. In addition, we have seen different types of alloys, compounds and elements. To classify these substances Based on their magnetic properties, let us discuss the basics of magnetic properties. We know that matter is made of atoms and atoms are made of electrons and nuclei. We have seen that a circulating electron in an atom has a magnetic moment. The resultant magnetic moment of an atom is the vector sum of the magnetic moments of all such circulating electrons in the atom. Here, the magnetic moments of these atoms in an object are randomly oriented and their net magnetic moment is zero. When the object is placed in an external magnetic field, the magnetic moments of the atoms are aligned partially or completely in the direction of the applied magnetic field. Then, the net magnetic moment of the object is in the direction of the external magnetic field. Thus, the net magnetic moment per unit volume is called magnetization or intensity of magnetization. That is, I is equal to m by v. The unit for intensity of magnetization is ampere per meter. Its dimensional formula is m0, L-1, T0, A1. When an object is placed in an external magnetic field, the total magnetic field inside the object is the sum of the applied magnetic field and the magnetic field due to the magnetization of the object. To discuss this more explicitly, let us consider a long current-carrying solenoid, where B0 is the magnetic field in the interior of the solenoid due to the current passing through it. When a magnetic material is inserted into the solenoid, the material gets magnetized. In such cases, the total magnetic field inside the material is the sum of magnetic field due to the current carrying solenoid and the magnetic field due to the magnetization of the material. That is, B is equal to B0 plus Bm, where B is the total magnetic field inside the material, B0 is the magnetic field due to the current carrying solenoid, and Bm is the magnetic field due to the magnetization of the material. Let this be equation 1. The magnetic field due to the magnetization of the material is directly proportional to its intensity of magnetization. That is, Bm is directly proportional to I. This equation can be further written as Bm is equal to mu0 into I, where mu0 is the magnetic permeability of vacuum. Let this be equation 2. Now let us introduce a new vector quantity called magnetic intensity, denoted by H, where H is equal to B by mu0 minus I. Let this be equation 3. The units and dimensions of magnetic intensity are the same as that of intensity of magnetization. That is, the SI unit of H is ampere per meter, and its dimensional formula is M0, L-1, T0, A1. On rearranging the terms in equation 3, we get the total magnetic field inside the material B is equal to mu0 into I plus H. Let this be equation 4. Now, the total magnetic field inside the material is redefined in terms of I and H. That is, the external magnetic field applied on the material, represented by H, and the magnetic field due to the magnetization of the material, represented by I. The contribution due to the magnetization of the material I is influenced by factors such as the nature of the material to be magnetized and the applied magnetic field. It can be expressed as I is equal to chi into H. Let this be equation 5, where chi is a dimensionless quantity called magnetic susceptibility. It depends on the nature of the material, which represents the degree of magnetization in response to an external magnetic field. The value of magnetic susceptibility is small and positive for paramagnetic materials. It is small and negative for diamagnetic materials. Substituting equation 5 in equation 4, we get the total magnetic field inside the material B is equal to mu naught into chi H plus H. That is, B is equal to mu naught into 1 plus chi into H. Let this be equation 6. But the magnetic susceptibility and relative magnetic permeability are related as mu R is equal to 1 plus chi. Hence, in place of 1 plus chi, we can write mu R, and we can further write equation 6 as B is equal to mu naught into mu R into H. Let this be equation 7. We know that the relative magnetic permeability is the ratio of the magnetic permeability of the material to the magnetic permeability of vacuum. That is, mu R is equal to mu by mu naught. Then, mu is equal to mu naught into mu R. On substituting the magnetic permeability of the material, mu, in equation 7, we get the magnetic field as B is equal to mu H. Let this be equation 8. The three quantities, magnetic susceptibility, magnetic permeability, and relative magnetic permeability, are related to each other, and only one of them is independent. If one of these values is given, the other two values can be determined easily. Let us have a look at the magnetic susceptibility of some elements at 300 Kelvin given in the following table. Here, it can be seen that in the case of diamagnetic substances, the value of magnetic susceptibility is small and negative. And in the case of paramagnetic substances, the value of magnetic susceptibility is small and positive. First, let us learn about magnetic compass. A magnetic compass, or compass needle, is used to find the direction of a magnetic field at a given point in a horizontal plane. It essentially consists of a magnetic needle, which is placed on a pivot in the horizontal plane. Thus, a magnetic compass can move only in a horizontal plane. When the magnetic compass is placed in a horizontal plane on Earth's surface, it aligns itself along the direction of the horizontal component of the Earth's magnetic field at that point. Or, it can be said that the needle aligns itself along the magnetic meridian at that point. At some places, the deposits of magnetic materials inside the Earth cause the magnetic compass to deviate from the magnetic meridian. At such locations, the angle of declination at that point helps us to determine the actual direction of the north. Let us now discuss the deflection of a magnetic compass placed at either of the two magnetic poles of the Earth. At the poles, the magnetic field lines either converge or diverge vertically. Hence, the horizontal component of the magnetic field is negligible. This means that the needle can effectively point in any direction. Thus, in terms of the path-finding ability, the compass is rendered useless at the poles. In such cases, a dip circle is useful. Dip circle is basically a magnetic needle pivoted in such a manner that it is free to move in a vertical plane. We can thus measure the angle made by the magnetic field with the horizontal plane. In the case of poles, this needle points downward, and as it approaches the equator, the needle aligns in the horizontal direction. Let us now discuss about the Earth's magnetic field. The Earth's magnetism is largely attributed to iron and nickel ions present in the hot and molten core of the Earth. This theory gains force from the fact that the Moon does not have a molten core, and hence it does not have a magnetic field. Venus has a slower rate of rotation and a weaker magnetic field compared to Jupiter, which has the fastest rate of rotation and a very powerful magnetic field. Although magnetism is attributed to these circulating currents in the core of the planets, the energy required for sustaining these currents and the causes for this is not very well understood till date. These are still interesting research topics. In fact, the path of the solar wind, that is, the stream of charged particles emitted from the sun, produces some magnetic field, which interacts with the Earth's magnetic field. Therefore, you can say that the Earth's magnetic field influences the solar wind. The pattern of the Earth's magnetic field is noticeably different at the poles than from the rest of the Earth. In fact, there is evidence that the Earth's magnetic field changes prominently in the short term, which is in centuries, and long term, which is over a span of 1,000,000 years. The dip angle at London varied by 3.5 degrees in a span of 240 years. That is, from 1580 to 1820 AD. This indicates that the position of the Earth's magnetic poles varies its position with time. Hence, it is observed that the Earth's magnetic field has even reversed the direction during long-term changes. Let's begin with permanent magnets. Permanent magnets are substances that can retain its ferromagnetic property for a long period of time at room temperature. Let's discuss the properties of a material used for making a permanent magnet. We cannot make permanent magnets from all types of materials. The hysteresis curve helps us to select a suitable material for it. The material should have high retentivity in order to retain its magnetization for a long period of time and increase the strength of the magnet. The material should have high coercivity so that it does not lose the magnetic property during temperature fluctuations, unwanted or scattered magnetic fields, and minor mechanical damage. Also, the material should have a high relative magnetic permeability so that it can be easily magnetized. Thus, taking into consideration of all the properties, steel is the most suitable choice. The other suitable materials are alnico, cobalt steel, and taconel. There are different methods of making permanent magnets. In method 1, we can prepare a permanent magnet by holding a steel rod in the north-south direction and hammering it repeatedly. This is an age-old method of magnetization. In method 2, hold the steel rod and rub it with one end of a bar magnet repeatedly in a particular direction. Thus, a permanent magnet is formed. This method of magnetization is known as single-touch method. However, the most efficient method of making a permanent magnet is to place a suitable magnetic material in the core of a solenoid and pass direct current through it. Thus, the magnetic field due to the current-carrying solenoid magnetizes the material placed in the core of the solenoid. This method of magnetization is known as electrical method. Permanent magnets have many applications, such as in magnetic door stoppers and magnetic screwdrivers. Now let's discuss the making of electromagnets. The materials used in electromagnets should have high magnetic relative permeability and low retentivity. However, the hysteresis loop for this type of material is narrow. Considering all these properties, soft iron is the most suitable material for making electromagnets. Place a soft iron rod in the core of a solenoid and pass current through it. The magnetism of the solenoid increases by many times due to the soft iron rod in the core of the solenoid. When the current through the solenoid is switched off, the magnetism due to the solenoid is also switched off because of low retentivity of soft iron. Thus, the electromagnets are referred to as temporary magnets. Electromagnets have their usage in many applications, such as electric bell, loudspeakers, and telephone diaphragms. Huge electromagnets are used in cranes to lift bulk quantities of iron, steel, and machinery.